So what we built is a brain-computer interface device that we call the bioelectronic interface system to Cortex. Brain-computer interface devices are important for people that have various neurological conditions, things that cause disruption in motor function, in speech. People that have had strokes, for example, their brain function is intact, but they've lost the ability for the brain to connect to the rest of their body in some way. And so what brain-computer interface devices do is they allow you to make that connection. You can now use the electronics to restore that lost function. So most brain-computer interface devices follow the more traditional paradigm for medical electronics, which is they have a relatively large amount of electronics that are embedded into a canister that's implanted in the body. What we've done with BISC is do something dramatically different. We don't have a canister. All the electronics are instead contained on a single integrated circuit chip, thinned down, mechanically flexible, that can fit directly under the skull, under the dura, right on the peeled brain surface. And that includes the radio, the wireless powering, the data conversion, all of the analog electronics. We have 65,000 electrodes on the system. We can record from 1,024 of those simultaneously. We can stimulate from over 16,000 as well. It communicates with a very high bandwidth radio to an external relay station that sits directly outside of the skull as a wearable.
This continuously powers the chip externally. By doing so, we don't need the battery in the brain. That's why we can make the chip so small.
It records data from the brain, transfers this outside wirelessly, no wires at all, no penetration of the brain, and you can see the signals all coming from the chip into our wearable device. And you can see here 16 channels in parallel.
What we've in fact built is a very high bandwidth connection between Wi-Fi and the brain. The surgical procedures that we've used to implant the BISC have been developed in collaboration with Brent Youngerman in our Department of Neurosurgery here at Columbia. We had to pioneer several different surgical approaches to being able to implant this device. And then we reached a point where we could actually do the surgical implantation in minutes.
When you see the BISC device and you insert it and put it on the surface of the brain, you're completely amazed that something that looks like a postage stamp has all of those technological components completely built into the device. And so this is a much more minimally invasive, appealing option for patients, and it also dramatically simplifies the safety and efficiency of putting the device in. BISC also offers incredibly high resolution, high throughput recording and stimulation. So that opens up possibilities, not just for the things that we're currently treating like Parkinson's disease and epilepsy, but it actually allows us to decode the more complex signals in the brain, motor functions or speech functions for patients with severe paralysis, tetraplegia. It would also potentially allow us to actually put electrical signals into the brain for things like restoring vision or hearing in patients with blindness or deafness.
This project was a highly collaborative project. One of those main collaborators was Andreas Tolius, and we worked on many experiments in visual cortex in his lab. He's also expert at many of these AI models that are trained on the data that comes from these kind of neural recordings.
We've shown that it has very excellent results in terms of reading information from the visual cortex, motor cortex, and we're very excited to show its capabilities in terms of writing information in the visual cortex for the application of blindness. We're also very excited to see it being tested in humans in areas like motor decoding and speech decoding.
BISC, even though it's a surgical procedure, can be relatively easily implanted and removed without damaging any brain tissue. If BCI devices can be brought to the point where the surgical implantation is a low enough risk, then you could imagine it could be something like a LASIK procedure, and you could imagine now using these devices to augment function rather than restore function.
The aim is to improve the quality of life of people with disabilities by establishing a really robust, high bandwidth channel between the brain and the outside world.
What we're doing with BISC is really taking this to the limit, to make a device that directly interfaces to the brain, leveraging the ultimate in integrated circuit technology, building all of that function onto a single integrated circuit chip.